All right. Welcome to the third instance of this Delta Lake tutorial. So the way this is going to work is that the URL on the screen has all the instructions that you need to do to set up your free Databricks Community Edition account and the instruction says how to actually download and import the notebook. You have the option of trying it in Scala or Python. In this tutorial, I'm going to show it to using Python, but you can do it in Scala as well. It is exactly equivalent, both the notebooks. And you have to use it. You have to create a cluster with the version Databricks Runtime 6.1 and attach it to the notebook. All the instructions are there in this URL, and this URL will be present in every slide that I'm going to present for the first 10 minutes while you guys set up. OK. Let's refresh what we have learned about data lakes since yesterday. So the promise of data lake was, over the last decade, people started building data lakes because they wanted to collect everything and store it in their giant data lake, and then do all sorts of analysis on top of it, not just SQL, but machine learning, AI, any kind of analysis they want. And so this essentially democratized data to a much larger audience than SQL analysts and BI analysts. But the problem is that over time, people realized that the major problem of collecting everything is that if your data originally is essentially garbage, corrupted data, unclean data, dirty data, and you collect everything without any sort of filtering or without any sort of gating on the data, then you end up storing garbage, which ends up resulting in your analysis and results being potentially garbage. And so to understand this a little bit more detail, let's understand what a typical data lake project looks like. And we'll understand this by understanding how, when Databricks started building our logging pipeline to collect all the logs of our services and do analysis on them, what are the problems we faced. And we believe that a lot of the people, a lot of our customers, and anybody who is trying to build such a data lake project actually faces a similar set of problems. So we were getting our logs through Kafka. And what we wanted to build streaming analytics to understand in real time what's going on in our Spark clusters in the cloud. We wanted to do historical analysis, so we wanted to dump the data in a data lake for long-term storage and build reports out of it. So we started first by building actually the streaming pipeline using Spark structured streaming. It was great. It has nice APIs and stuff. But that you could only store maybe a few days or at most few months of data in Kafka before it was not getting very efficient. So we had to, for longer-term storage across months and years, we had to build another pipeline using Apache Spark that dumped data into data lake. And from there, we could do long-term reporting and other kind of analysis, AI jobs, et cetera. OK, so this was basically Lambda architecture that we built. That was the cool thing to do back then. We built that. But soon we realized the problem of Lambda architecture is that you had to, they could have different logic, and you had to cross-validate between them, because they may deviate over time and do different kind of processing, which is not, and it becomes hard to reason about. So you have to continuously cross-validate. And while cross-validating, what may happen is that you realize that, oh, there is some difference, so you have to reprocess some of the data. In fact, often reprocess and fix a lot of the data to optimize it by repartitioning it and things like that. And while there is all sorts of writes going on, reads going on, and that leads to complexities on how do you understand what is being read when things are being modified at the same time. Furthermore, we realized for GDPR purposes, we had to take the data and long time later actually delete stuff from it, update stuff in it. And that, again, leads to sort of complication that you don't want to delete stuff while the report is being generated, because you don't know what gets read by the reporting job. And so you have to do this dance of, at midnight, I'm going to run my delete job, and then at 2 a.m., I'm going to run my reporting job just to avoid them being run concurrently and stuff. So basically, we were wasting a lot of money and time, of course, to solve these system problems, which is unrelated to the data and which is taking time away from extracting value from the data. And so to summarize, the key problems were there was any complete lack of atomicity when there are concurrent workloads reading, writing from the same location. There was no quality information, so you could dump garbage data or wrong data with the wrong schema or corrupted data into the directory, and and it becomes very hard to reason about how to undo that. And then when you're reading, writing, there's no consistency in isolation, so complete lack of ACID guarantees. So that's why we went ahead and built Delta. So let's see how it looks like with Delta. So from this pipeline, it became something much simpler. So we essentially unified our batch and streaming pipelines into a single pipeline. We sucked all the data from various different sources and dumped it as bronze tables, which is a raw table, unfiltered, but has everything. Then over time, we filtered to the next layer of silver tables, filtered, cleaned, et cetera. And then the gold tables are aggregated value data on top of the silver tables, which is directly consumed by reporting jobs and streaming analytics. So from left to right, essentially there is a clear increase in the quality of the data. And throughout that, in every step, you have full ACID transactional guarantees, which is why you can reason in an end-to-end manner that the reports that you're getting contains all the data and the correct data that is being consumed at the left end. Finally, all of this we built on top of open standards and open formats. And yesterday we announced that we are contributing a Delta Lake project to the Linux Foundation. So this is all open. There is, as a customer or as a user, there is no lock-in at all. And we designed the whole entire thing to be consistent between batch and streaming. So the entire thing could be built in using either batch or streaming, and we seamlessly mix batch and streaming workloads with full transactional guarantees. And we added support for all the necessary DMLs like update, delete, merge. Again, full transactional guarantees. You can reason about what you're getting out on the other side, and you can do much more advanced stuff like change data capture, GDPR, deletes, and stuff. Anyway, so those are some of the large number of benefits of using Delta Lake. So, and right now Delta Lake is being used by thousands of Databricks customers, as well as a growing number of organizations in the open source side as well. And together, our customers processed more than 2 exabytes of data in the last month alone. So it has a pretty large and very stable user base at this point. So at this point, I'm guessing that everyone who wants to try out the hands-on tutorial has signed up. Does anyone have any problem regarding this thing? If you have any problems, my friends and colleagues here are ready to help you out. Just raise your hand. OK, good. OK, so let's actually switch gears and actually start working on the notebook. So, oops. OK, so here I'm actually going to use the Python tutorial notebook. So the first step is that we have actually, the data that we use is data from this company called Lending Club. Oh, huh. OK, hold on. Maybe it'll work now? Yes. OK, good. So the data we are going to use in this notebook is from this US company called Lending Club, which essentially manages loans across individuals and companies. And this data set has data from loans given between 2012 and 2017. So for the purpose of this tutorial to run on the Databricks Community Edition, we have scaled down the data into a much smaller filtered data set. And we have hosted the data set in a location that this will automatically download if you run this cell. So it is actually spinning up the cluster, preparing it, and it's going to, yep, now it's going to run this cell. And there it downloaded the data set into a location. I'm going to run a few more setup and configuration things to clean up the directories so that we can start from a clean slate. And now, OK, Now is the real first step. That first, we're going to see that if we try to process this data as a Parquet table, what are the problems are we going to face? So in this cell, I'm actually deleting the Parquet table if it exists, and actually creating a brand new Parquet table, and it is named as loans Parquet. There you go. Okay, so let's actually explore what is in the Parquet table. So there are essentially 4 columns in this Parquet table: the unique loan identifier, the amount of the loan that was given out, and the paid amount, how much of that loan was paid. And this is the US state where this loan was made. So let's see how many records does it have in total. 14,705. Okay, 14,705. Okay. So this is, you can ignore this for now. Okay, so let's try to work on this data. So let's say we have a stream of more data coming in, more loan information coming in, and we want to append that stream of loan information all the way into this Parquet table I've made. So for that, I'm going to define a few methods. Here I'm defining a method to use structure streaming to generate streaming data frames. And I am hoping that everyone is familiar with structure streaming. If you're not, please take a look at my previous talks to understand about structure streaming and how to make it work. But the brief idea is that here I'm creating a streaming data frame with 4 columns with randomly generated data. And then I'm saying that I'm going to write it out in this case, Parquet format, and trigger it in 10-second microbatches and start. And then there are other methods to actually stop the streams and clear up all checkpoint directories and stuff. So here, let me mention that it is important that you remember to call this stop all streams and not let the streaming queries run for a long duration, because Databricks Community Edition has a limit on the number of files you can have in your account, since it's a free account. And if you run your streams for, say, half an hour, you are going to easily run out of those files, and you'll have trouble cleaning them up. So for the interest of not facing those problems, let's remember to stop your streams after running it for a few minutes. OK, so here I've defined everything, and then I'm going to actually start running the streaming query. So it is initializing the streaming query. It is figuring out from the streaming data frame, it's figuring out what is the logical plan, converting into a sequence of physical plans, and then it starts to running. So here, as it's initializing and running a few batches, here I can see that it's running roughly somewhere between 5 to 20 records per second. OK, so let's see whether the table data, the number of records in the table is actually growing or not. OK, I had 14,700 records. What happened to that? I just see only 90. What happened to the table? Let's actually look at what the table contains now. Something is going wrong. OK, wait a minute. So earlier I had 4 columns. Now I have more than that. This timestamp column and value column, these are 2 new columns that came out of nowhere. I really don't understand what has happened. So really what happened underneath is that the streaming data frame that I created to generate fake data, I created 4 columns in that with fake data in it. It actually had 2 more columns that I didn't realize while writing the query, and it started writing new Parquet files using 2 extra columns, which it was not intended. It was accidentally a mistake. But nothing in the Parquet table stopped me from doing it. So now suddenly I have data in the directory that one has 2 extra columns, which I didn't intend, so therefore effectively corrupting the Parquet table. And it completely ignores any of the previous data that was present, because it is only counting the new record that has been added by the streaming query. And this is because, I'm going to stop the stream first. And this is because working with Parquet has two major problems. Since Parquet is a file format only for a single file, it just defines the layout that is made within a single file. It doesn't have any semantic information of how to manage data across multiple files over an entire directory. So there is no enforcement of schema. You can just dump different types of Parquet files in the same directory. Nothing will stop you. And there is no semantics in Spark and Parquet to allow interoperability between batch jobs writing to the same directory as streaming jobs. So this is why you cannot mix different kind of workloads in the same location. Rather, on the other hand, let's actually try out the whole thing using Delta Lake. So for that, I'm going to actually recreate the data from the original files I downloaded into a new Delta table called loans Delta. OK, so here, let's actually look at the data once again, just to be sure whether I have all the expected data or not. Yes, I have 14,705 records, and I have the 4 columns that I expect. OK. Yes. Sure, go for it.
The first Parquet.
Yes.
You call them merge schema, so that would merge the last Parquet with the original ones, and just put null on the other 2 columns of the original file, so that you would get that.
Good question. So the question was that what happened when you actually started writing Parquet new data with 2 extra columns? Did it merge with the previous existing Parquet files, or did it add nulls to the previous ones or not? So what happened is that the existing Parquet files just continued to be there untouched with 4 columns, and the new Parquet files got added with 6 columns. And now when Spark is trying to read both of them, it will do a schema merge across them, and the merged unified schema will obviously take into account the new columns as well, because it doesn't know anything better. So that's why it will look like all of them as 6 columns. And when you're trying to read using that 6-column schema, the old Parquet files, it will show up, the new columns will show up as nulls, because that data isn't there in the old Parquet files. So that's some of the problems.
But then your count would be correct.
Your count in this case is not correct, because Spark, structure streaming, and Parquet together does not have the additional metadata needed to merge old batch data and new streaming data. That's the problem. So let's actually take it a step further. Let's actually, instead of writing a batch or an interactive job to get the counts, let's actually write a streaming job to continuously get the updated counts. So here I've read the Delta table as a read stream, and I've said on this, define it as a table loans Delta stream, and then call select counts on it. So in this case, what it'll do is that it'll continuously monitor the table and to Delta table to see if there is any new data and incrementally count it. So in this case, as expected, we have 14,705. Now let's try running that same streaming query again. I'm going to use that exact same function that I'd used earlier, but instead I'm going to write it using Delta table format. But here, it is actually stopped me from writing. This failed because it detected that the data frame that I was using to write has a different schema than the one in the Delta table. So, and it actually gives the information that the data schema that I'm trying to write has these 2 extra columns where the table schema does not have. So it actually blocked you. It's enforced the schema and blocked you from writing corrupted data. So now, let's actually take the next step, and let's actually fix our query to see if actually it works. So here I've actually copied the function once again and fixed it by actually selecting only the columns that I want. And rest of the code actually remains exactly the same. I'm going to define it and try running the query using the new function. So it's starting it once again, and now you will notice that it actually started. It is actually processing, because now it knows that the schema is exactly correct. It is allowing you to write actually and append to that table. Now, so now another cool thing is that another thing that structure streaming plus Parquet cannot do is that multiple streaming queries is writing to the same location. Because again, it doesn't have the additional metadata needed to actually manage both the streaming queries and mix concurrent workloads, streaming, batch, anything. So, but here I can actually do that. I can actually run another streaming query. But before that, let's see. It is actually updating the counts continuously. And it has combined the previous batch data and the new streaming data, and it's counting continuously together. So now if I actually run another streaming query using the same fixed function, it will actually run. And if you notice it carefully, then this count will start growing up faster. I mean, you have to look at it for a while to really understand that, but I think you can do it on your side. But yeah, it is the count of both the streaming queries and the previous batch data that has, it is accounting for everything. And just for sanity check, let's actually run the batch job or the interactive job to count as well, just to make sure that it can still mix it. So there, it is the updated count, it includes the previous batch data. OK, so before I forget, let me actually stop all the streams. So now, so you have seen schema enforcement that will going to block you from writing bad data. Now let's see schema evolution. So that is when you actually know that you have extra columns and you want to evolve, change the schema of the delta table. That is when you can actually do it by using this option called merge schema. So here, let's say I have two new loan information where I'm trying to add an additional column saying closed or not, based on whether the loan has been fully paid or not. And here in this case, I have two new data where the funded amount was 1,000, paid amount was 1,000, so closed is true. Whereas in this case, nothing was paid, so it is not closed yet. And so I'm going to create a data frame out of this data and write it in the delta format to the same location with this option, merge schema equal true. And there it figures out that, oh, there is a new column, which is, and this, the new data frame is different, but the new column, and I can very easily add a new column. It is an acceptable evolution of the schema. It's simple to add a new column. And so it did add it and allowed the write to happen. So now you actually, if you query it, there, the new column is there. And for all the existing data, the value of that column is null because the earlier Parquet file doesn't have it. You can run another update query or something that we'll talk about later to actually update the value of that column for the other rows now. Anyways, so let's actually summarize what are the things that we learned here. So Delta Lake has full support for mixed batch and streaming workloads all running concurrently with full transactional guarantees. You have schema enforcement, and when you want schema evolution, and of course, everything ACID transactions. OK, so let's move forward. Let's look at the third thing that we want to show today is how to delete from Delta Lake. So let's say you want to delete all the funds that has already been paid off, so essentially all the closed ones. Let's see how many funds out of that 14,000, or wait, 19,000 now, are actually paid. So it's 5,134. So let's say I want to delete off all those rows from the table because for, let's say, GDPR reasons. All we have to do is take this delta path, create this object that called delta table for this path, and using this object, and this is essentially outside Spark APIs because Spark APIs does not have the concept of delete. We had to create these additional APIs to support delete and update and merge programmatically. But once you can create this object called delta table from given a path, and that object has this method called delete. You can provide the predicate of what to delete. And this is exactly like the SQL delete command. And so if you run this, and then see the count once again, it ran. Therefore, there is no more loans that have been paid. Now, interestingly, the fact that those loans got deleted does not entirely delete it from the entire, actually the storage, from the directory, because delta table essentially maintains multiple versions of the data. So because it uses multi-version concurrency control, so that readers can read a previous version of the delta table while the writer is updating the table. So it maintains a full history of different versions until you actually explicitly clean it up. And to see what are all the previous versions, we have this method called history, again using the same delta table object, this history, which shows all the previous versions. Here, for example, these are all the operations that happened on the table. So earlier you can see that there was all the operations were streaming updates, all the appends were being made. You can see that there were 2 different query IDs. These are the 2 streaming query IDs are uniquely identified different streaming queries. There were 2 different streaming query IDs that were actually appending to that table. It did it from this notebook. I appended it. And after that, there was this one write with the one write that I did to evolve the schema, to add the 2 new rows. That was that one write, and now I deleted it. Now, I can actually use this version number or the timestamp to actually query the previous version, because all the data is there in the directory. So that's how you can travel back in time, by actually specifying the version as an option in the Spark DataFrame reader and stuff. The version of this thing. So I'm using the history command once again to find the latest version. History 1 gives just 1 row of the history in reverse chronological, so that's the latest version. And I'm finding that version and computing the previous version and using that. I'm actually going to read the delta table using this option, and there I'm querying it to find the number of fully paid loans, and there we got their data back, 5,134. So you can go back and query previous versions. If this delete was actually accidentally done, you can actually roll back by actually reading the previous version and overwriting the table. You can do all sorts of auditing based on and tracking on who accidentally deleted what, or who accidentally updated what. You can do all of that. Now, in this case, we know that the delete is actually a valid one. And in fact, I wanted the data to be actually deleted off completely from the storage, from all previous versions, because for GDPR compliance, the data should not exist anywhere at all, right? So here, for that, we have this operation called vacuum. And what vacuum does is that it will, based on a retention window, let's say, which by default is 7 days. So if you run vacuum, using that against that delta table object, if you just run vacuum without specifying anything, it will basically delete off all the unnecessary data files that are not needed by last 7 days of table versions. So, and in this particular case, this table was created not 7 days ago, few minutes ago, so there isn't 7 days of history. So, all I want is to maintain only the latest version where the deleted data is not there. So I'm going to use vacuum 0, say retention hour is 0, to actually delete off the data files required by all previous versions, but not the latest version. And so now if I run that same query above, using the same previous version option and stuff, it will actually fail because the files have actually been deleted. It cannot read the file. But this is the entire workflow of delete and verify, audit, vacuum when needed. OK, wow, this is a long error message. OK, the last thing we're going to talk about is merge. And merge is some of the most complicated workloads are best expressed as a SQL merge, where you have to basically, based on a different data set, between 2 tables or a data frame and a table, you want to, based on a matching common key across them, you want to update some of the rows and insert some of the rows that is not already in the table. So that kind of absurd thing. Now with Parquet, we tried to do this, and this was a pretty complicated 7-step process to do joins to identify what are the rows matching, which are the rows not matching, which are the new rows, et cetera, and write it to a temp table and union them and all of that. Instead, we just supported the merge operation. And what it does is does all of this in a very simple manner. So let's say I'm going to recreate the delta table with a much smaller number of rows to understand what rows got updated and inserted. So I'm going to run this this query once again to actually take the, whoops. I try and find. Anyways, so I took only the first 3 loans from the actual original data and they wrote it out into a delta table. I actually, let's see actually that. Yeah, so there are only 3 loans in the table. Now let's say you want to update it by saying that the loan ID 2 has has been fully repaid, so the paid amount should be 1,000, and a new loan was added which hasn't been paid. So let's define the data. So here I've defined loan ID. The paid amount for 2 is 1,000. For the new data, there is nothing has been paid. I'm going to define this data frame. Here I've defined it, and then actually call merge. Again, using the same delta table object, I'm saying that loan updates is the data frame I created. Delta table each has an alias of TNS. I'm saying the match with the common loan ID information. If it matched, then update that row in the table. If it did not match, that means that it's a new loan. Then insert all the columns in the table. So if I execute it, it will actually figure out which files in the table have data that actually needs to be updated and accordingly rewrite those files. And then now if you look at the table once again, yes, 2 has been updated to 1,000, and 3 has been updated has been inserted. Okay. Now, the cool thing is that the standard SQL syntax of merge only supports update and delete. You have to specify what an update clause and an insert clause. But we support a much larger extended syntax of merge, which very few systems in the world, even more so very few open source systems in the world actually support. And what it allowed you to do is basically we allowed you to do when matched delete. You can specify when matched and additional conditions on that. You can even eliminate things like you don't want to insert anything, you just want to update. Or if you don't want to update anything, you just want to insert. So when not matched, then insert. When matched, just ignore. So that kind of stuff, a lot of this can be done. And that actually enables a lot of complex use cases essentially, you can use this entire thing from a streaming query. Suppose in a streaming query, actually, that is what I'm going to show here. So let's say, using the state information that I have in the table, I want to continuously compute the number of loans that are present in each state. And I want to do it continuously, therefore I want to do it using structured streaming. And I want to write out the continuously updated aggregate into a delta table, so that is my, let's say, gold table, so that I can directly use that table for reporting how many outstanding loans are there across the states and stuff. So here, for that, all I've done is, so in the instance, I won't go to the nitty-gritty details of how I've defined the streaming query here, but I'm going to run through it. But here I've done to generate fake data, randomly generated data. Here I have defined this method called upsert state counts into delta table. And what this method does is that given a data frame with updated counts, it will actually use merge to upsert it into the delta table. Now, once I've defined this method, in structured streaming, there is an operation called for each batch, which what it does is that in structured streaming, it runs in micro batches, right? So the output of every batch, it can apply arbitrary function on the output of every batch. And in this particular streaming query, I'm generating fake data, but ultimately I'm actually computing the counts for every state, grouped by state and stuff. And then finally calling for each batch with the function that I've defined that can take the updated counts and upsert into the table. And I'm using for each batch to essentially use that function, which means that in every batch, the counts of each state that got updated will be upserted into the table. Whoops, oh, I didn't run this. And then, so I'm actually starting this query. So once I start this streaming query, it's actually initializing, it is computing the counts, generating data and stuff. So now it was actually writing to this new location, loans count states path, and I'm going to do a batch query on that location. You can see the counts are being generated for 4 states. Now if I run this cell multiple times, you will see that this state is continuously, the counts are continuously being updated. I think every 10 seconds. Yeah, okay, the counts are being continuously updated. So this is, and this is very powerful because any kind of aggregation or sessionization or advanced complex aggregations you can do in structured streaming, you can output it directly into a table that is ready for for reporting and stuff as a goal table. Cool. And I'm going to stop the streams. So now, there's another example. I'm not going to go through in the interest of time, but as I said, merge, the extended syntax for merge enables a lot of different things. You can do data deduplication directly using one merge query. Basically, when matched by a common deduplication ID, only insert, no need to update. Then we can do SCD type 2 type operation where you want to maintain the entire history of a particular user, which is on dimensions that are slowly changing and stuff. You can do change data capture, and this is very useful because a lot of our customers, a common workload I've seen is that they have a OLTP database for quick transactions, and they want to replicate that OLTP database continuously into a OLAP table in a data lake so that they can run analytics queries on the OLAP table without affecting the performance of the OLTP table. And you can use merge to automatically and merge for each batch to continuously apply change data to the OLAP table. Anyways, so you can run it yourself. So anyways, to summarize before we finish the whole thing, what we have learned is Delta Lake has full support for batch and streaming workloads, including concurrent mixed workloads with full transactional guarantees. You have schema enforcement, schema evolution. You can use the entire history of all the previous versions of the table to audit, roll back if needed, and time travel, etc. And then finally, you can actually use vacuum to completely delete off the previous versions after you have run a delete operation, and you have merge to do even more complex workloads like change data capture, SCD type 2, simple upserts and stuff. Anyways, so we have a pretty active community right now, especially on Slack. We're trying to be diligent about answering your questions as fast as possible across the 24/7. We are seeing that a lot of not just us in Databricks, but all other people on the community are also starting to answer questions on behalf of us when we are asleep. So it's actually pretty cool to see the growing Slack community. We also have the public mailing list for slower communication, as well as we look at GitHub issues when people report actual issues on GitHub when using Delta Lake. So please join the community, and we're hoping that Delta Lake can actually solve a lot of your problems as it has done for us and our customers. Thank you.
All right, thanks, TD, for the introduction, for the tutorial. We have a couple of minutes for questions, if you have some. Otherwise, proceed to the break.
Yes. Good question. Let me repeat the question. Can we specify the retention of the vacuum in terms of number of versions to retain, or does it have to be always with time, right? Yes, as of now, it has to be always related to time. But yeah, that is something that we can work on. That is something, if the community wants something like that, I mean, we're totally welcome. It's all open source right now, so you're totally welcome to contribute that feature.
Thank you. Earlier in the talk about Delta Lake's use with Zalando, one of the problems was brought up that when you merge data, you gradually get a problem that if you merge an increasingly small number of records on a very large set of records, it becomes quite difficult in terms of performance. Do you have any strategies that we could or should look at to avoid that, particularly if sort of data is time sensitive and only more recent data is changing? Is there any approach that can be chosen?
Very good question. So for merging small data on a large table, yes, that is. So the way merge works underneath is that it does two passes on the data. First pass is an inner join that joins the two tables, DataFrame and the Delta table, to identify which files actually contain the matching records, and then does another pass to actually modify those. Now, we essentially rely on the performance and the optimizations that Apache Spark has to optimize those joins in those cases. small table joining with large table and stuff. Now, Apache Spark has a lot of optimizations already doing that. So, and we are hoping that we can continue improving Apache Spark for doing that. As you can see, I think if you were at the keynote yesterday, we announced that we can do a lot of dynamic pruning, et cetera, in Spark 3.0. So that is definitely going to continuously improve the performance of merge automatically.
Yes, hi. I had a question as well over here.
Sorry. Oh,
Hi.
there you go.
Yeah. I had a question regarding if you use a Delta table as a source for your streaming job and then put it out to another Delta table. I saw in the documentation that if you do an update or a delete using merge in the source Delta table, then it's not always a proper send it to the next Delta table. For example, if you have an update, it will be shown as a new record. If you have a delete, it doesn't show up. Do you have any tips or advice if you want to use merge on the source and then get only the changes to the the output table?
Very good question. So right now, we don't have support for getting a change log out of the Delta table at the granularity of the rows. Simply because right now, in the way it is implemented right now, we don't have a unique identifier for each row. So we just keep track of data at the granularity of files, not at the granularity of rows. So right now, we don't support a row-level changelog data. So I don't think we have a very clean, elegant solution for that right now. But depending on the use case, I think there are workarounds. For example, the major problem is that when you're not appending, but you're doing some other change, you're rewriting files, when you're trying to read from it, it doesn't know whether the rewritten file what data has changed in that. So it just says that I cannot do this. And now there are options to actually force it to read and consider all files written, irrespective of rewritten or not, as new data. And so which means that when you read from it as a stream, which is using that option, you will get duplicated data because files are being rewritten. So the new file will have the same data once again. So now, depending on the use case, it's OK to have duplicate data. For example, let's say you're reading from a Delta table and writing it and updating an OLTP table or a key value store to get the latest aggregate data. There, getting duplicates is OK. Semantically, it's OK. Maybe performance-wise, not the best because you're doing duplicate operations, but at least semantically, it is OK. And it also boils down to how frequently you're doing update, delete kind of non-append kind of operations. So you can work around that for now in many use cases.
Thank you.
All right, thanks everyone. We ran out of time. Sorry, we should take it offline, maybe the questions. But yeah, now we have a break and then we have more great talks afterwards. So thank you again.
Thank you very much.